perfect mechanical wave over a metre high, and you get one every minute of these. Now the science on display here could be changing the nature of surfing.
Pre-class, so you're welcome to talk amongst each other, but I see you're transfixed.
So how does it all work? I'm with Alex, the engineer. So tell us.
Okay, it's very simple. It's just the fluid that moves underwater, and with lagoon shape, we are able to create perfect waves.
Every time?
Every time.
For as long as you like?
So can you tell where he's from? From the accent? Wales.
Okay, so this is the control panel. We have information here that shows...
So these are wave pools. It's a lining and a pool and a wave, some kind of wave generator. It's in Wales, the western side of the UK, South Wales. They have them also in Australia, of all places. I guess in Australia, maybe you want to be safe from shark attacks. So they have them as a central pond with central wave generator, radial portions that go out, and you can vary the size of the waves, etc., for different levels of skill. And of course, you're relatively safe in them. You can control the size to practice. I note that in the Olympics, when they had surfing this year, they didn't do it in wave pools. They did it in Tahiti, French protectorate, I guess, in the South Pacific. But surfing, of course, is the same principle as we talked about surfing West Virginia, using gravity to climb down the wave. You're using the viscosity of the wave under the board to push you up the wave, and the balance between those puts you where you are laterally on the wave as you move across strike. So anyway, so interesting thing to look at. And I note that the Paralympics are on now, and one of the ladies, I think she might be an American young lady, lost her lower leg in a snorkeling accident with a shark. I guess not so much of an accident, but she's competing in the Paralympics as we speak. Don't know, is this going to come through? Is there sound? So this, well, you can see what's going on there, right? Is it? So this is just off Portugal. I don't know why it's not. This is why.
Pedal down out of control now. When you did Britain's Andrew Cotton harnessing a monster wave that could be the biggest ever ridden. He held his position for 10 seconds in an attempt to enter the record books. I'm sort of very focused on what you.
So this is off the coast of Portugal. There's some kind of canyon that comes in close to the shore, funnels the waves into it. They become these massive waves, and people go out there after storms to do this and beat crazy stuff. So I've surfed before in southwest of England, in Cornwall, on itsy bitsy waves. So I can't even fathom doing this. This is just nuts. But people choose to do it. I think it's quite incredible. So I'm not sure what else they have to say.
Record of 78 feet is held by Garrett McNamara, seen here off the coast of Ireland with Andrew Cotton last year. The mission is to surf the biggest wave in the world, and very luckily I haven't actually been doing too much plumbing, but no doubt when the summer comes I'll probably be back on the beach lifeguard and back on the building site.
Just a regular Joe, just got a trade job, and this is what he does for fun. Goes to Portugal and does it. I guess it's copyrighted to him. We'll see if in the, sometimes I get copyright claims come over YouTube saying you can't use this video. They must be stamped somehow, because they come very quickly as soon as I upload it. And finally, let's have a look at this. So this video must have started around the time of the Great Japan earthquake, I think March 11th or 12th, 2011. This is Eastern Japan at that time, and someone filming it. Of course, the safest place to be if a tsunami is coming in is to have your boat out at sea. We made the point before that tsunamis out at sea might be a few centimeters tall. We'll see in this video as we go through this, I'll let it run in the background as we talk about waves today, that there's some timing of the waves that come in. So this is someone that sounds like it's Kamaishi. It used to be the Pittsburgh of Japan. I visited there once through a small earthquake they had. I was in a meeting. And so it's seen better days. Steel has gone away. Steel went from Pittsburgh to Japan, to Korea, to China over the post-war years. And so this is an earthquake. They felt the shaking due to the earthquake. Almost nothing happened due to that in Japan because they've built all their buildings to guard against that. But what we still haven't, now we know, but we still haven't got a handle on is the problem with tsunami. And so this had a very big tsunami that came in. So we'll keep this running in the background. This is someone filming the whole thing in a parking lot. And so maybe we'll run with this in the background in PIP mode while I talk about some other things. So I'll turn off the volume, not that we've listened to it. My guess is that things start happening 20 minutes in. So I guess I want to go back out, and I want to go PIP. Well, I can tell you're just amazed by my extreme skill in all of this. Okay? So that's the eye candy for today. So we'll go back and talk about this. All right. Any issues we should take care of? Don't feel you have to, but I just thought I'd ask. Okay, introduce yourself to Derek bandwagon. We had Kalia, who didn't give me COVID. Different story, ask her about it. We've had Bobby. We've had Colin with the hat. We had Mohammed. We had the four guys before. We've had Elizabeth and Claire from Tyrone. We had Marcus. Come get a bit of the action. Come and see me if you wish to. I'd be happy to see you. Hope things are going well. You'll see that my style of doing things, it's almost, hopefully it's not quite like drinking out of a fire hose, but we go quite quickly through stuff. I didn't mean to be so disparaging about the book that I said you don't have to buy it. Of course you don't, because nothing that we rely on this course comes from it. But as third-year students, when fluid mechanics is kind of a foundational thing for what you do, and it's an important topic, I think you might be crazy not to spend $100 on it relative to the tuition you pay for this class, and perhaps even more so to not find it online somewhere and spend some time doing that and use it. The terminology we use here is absolutely the same, and I think if the course is easy, no brainer, you don't need to do it. But if you think you might have a challenge there, it might be worthwhile doing it. Yeah, and that's it. That's all I have. So remember that, Penn State idea is a class. It's 3 credits in the classroom. 3 credits is 3 hours in the classroom each week, and probably double or triple that in terms of doing stuff on your own. My style is not to make you fill up your schedule with busy work doing assignments, this, that, and the other. I'd much prefer that you do things that are probably useful to you. The class is built on assessments, right? So these midterms. So you should have downloaded the midterms. By the end of the week today, we'll have covered all the topics that we talked about in terms of fluid properties. You'll see that some of the first midterms relate to that. If I were in your shoes, I would take those tests, I would look at them, I would try and think about how I would solve them, not necessarily do it numerically, and then look at the solutions to see if I'm on the right track. And if I'm not, then learn from that. So I don't want to tell you how to learn. You've been doing it for 2 decades, right? 1.5 decades formally with books and math and conversation, and the first 5 years probably intuitively. But yeah, take charge of your own education. Okay, that's my paternalistic talk for today. I'll quit now. Okay. Anything else before I get going? Good. All right. Well, very quick recap on what we talked about last time. In terms of, is this up there? Let me get back. Okay. We talked last time about what a fluid is. It's a liquid or gas. Fluids can freeze and they become solids, but that's not what we're talking about here. A fluid is when you apply a force to it, it moves at a velocity, as we'll see today when we talk about viscosity. A solid, if you apply a force to it, it compresses and then stays static, doesn't move anymore. That's kind of the distinction. We talked about these properties of density, viscosity, modulus, and its corollary, which is compressibility. We'll talk a bit more about those today. We talked about dimensionality. You can always tell whether an equation's wrong if the left and right side don't match up in terms of dimensions. The dimensions we use, I'm not sure I did it very well, but we moved through it quickly. The 3 dimensions for SI units are mass, length, and time, and the units of those are kilograms, meters, and seconds. It's a bit confusing. The book uses T for time, but we also use in the ideal gas law T for temperature, as the book does, both of them. And so you need to be aware of that. So we can split any property up into its component parts, mass, length, and time, and then evaluate left and right sides. Some dimensionless parameters we talk about are useful. We have 2 different scales for both pressures and temperatures. If we use ideal gas equation, we have to use absolute pressures and absolute temperatures in Kelvin relative to absolute 0. Typically, in other calculations, we use gauge pressures. Gauge pressure for us here today, if you measured it, would be 0 kPa, but the absolute pressure is 101 kPa. And likewise, if we looked at the temperature today, it's probably a bit warmer than 20, it's probably 25, but it would be, in Kelvin, it would be 298, is that right? Plus 5? 25 and 298. And so we need to use those in the ideal gas law. We talked briefly about the ideal gas law. I hope you've thought about your cooking on Everest and to see that it makes sense. The idea is that water boils at a lower temperature because the pressure's less. If it boils at a lower temperature, it keeps at that temperature by vaporizing. Vaporizing releases the latent heat of vaporization, and that keeps the temperature from going up to higher. It stabilizes at whatever that rate is. And so on the top of Everest, it might boil at 90 degrees. And so the time to cook something relies on how long you stay at a certain temperature to be able to be cooked all through. It's Labor Day, a party trick. If you have a steak and you're going to cook it, it matters how long it takes time to get the heat of the burner into the interior of the steak. That's why you flip it. So if you have a 1-inch steak and it takes 15 minutes to cook, how long does it take a 2-inch thick steak? It scales with the length squared. So you can do a dimensional analysis. You can use a differential equation for heat flow. You can find that it scales with a time which is equal to thermal conductivity time over the length of the characteristic length squared. So if you double the length of the diffusion into the steak, then you L squared that length and it takes 4 times as long. So you can impress your party guests if you have a cookout over the weekend. Different curves on here. The vapor pressure are these pressures. Right on this vapor pressure, it means that the same amount of material is vaporizing as is condensing. It's at equilibrium. As you go above that temperature, then more is vaporizing than condensing. You can go across that line in a couple of different ways. You can change temperature, as in boiling water, and go to this side. But you can also reduce pressure. So if you're at some pressure, maybe not at boiling, but maybe at, this is a strange scale, I'm not sure where 20 degrees is, but if you're in the ocean at 5 degrees centigrade and you're in a submarine, then if you look at submarines, they have very big screws, very big propellers at the back. They're almost like airplane propellers. They're much out of size compared to a normal ship's propeller. The reason for that is that they can turn slowly and provide a lot of drive. If you turn them quickly, just like a wing, you get low pressure on the top and high pressure on the bottom. If the low pressure on the top is low enough to reduce the pressure too much, then you cavitate the water. You make it into bubbles, and bubbles burst, and bubbles can be picked up on hydrophones, and so you can't run silent, run deep as you'd like to. Likewise, I guess if you are skating, I suppose, and you're sitting on the ice rink, even if you're very petite, the stress on the skate is high because it's concentrated. It's putting all your weight on a 3 millimeter, 1/10 of an inch band. And so the pressure under your feet will go up. And if the pressure under your feet will go up, it has the potential to be able to melt it, just like a snowboard coming down a mountain. It melts a thin layer of the snow, that lubricates the motion, and you're able to travel as a result of that. So anyway, is Kamaishi still running or did it stop? Oh, it stopped. Fine. Perhaps it only just restarted now. So is that right? Is it at the beginning? Let's have a look. Yeah, it just started. Well, that's my bad. Never mind. Yeah, so get your watches on, 20 minutes. All right, what else do we want to talk about? We talked about the ideal gas law. That's it. Absolute pressure is equal to density. This is the gas constant for a particular gas number I. And this TA is the temperature in absolute. One reason you might want to look at your book, I don't use these notes very much, but in your book, if you have looked at it, there's a table that is this. It gives all these components in terms of mass length and time and force length and time, the two systems. It uses temperature. Here's theta. So T is actually time, not temperature. And so you can look at all these different units that we will use in this class, and they're classified there. And so that's a useful resource for you. Again, I encourage you to grab a copy of the book in whatever way you can get it so that you have a better feel for exactly what we're doing. So the other reasons that we might want to use the ideal gas law is we can look at compression of gases. This isn't working very well. Don't know why. And this isn't a thermo class, but you can compress things in two different ways. Isothermally, in which case you can write the ideal gas law as absolute pressure over density is equal to the gas constant for that particular gas times the absolute temperature. Obviously, if the absolute temperature isn't changing and you're compressing it in a bicycle pump, so in other words, you have a bicycle pump, maybe you put the bicycle pump below water to keep the outside shell of the pump same temperature. You push it, so what will happen is the gas will compress, the pressure will rise, and the density will increase. So if temperature hasn't increased, then this side will stay constant because temperature doesn't change, in which case absolute pressure over density is constant. So in your bicycle pump, if you double the pressure, then you double the density of the gas that's inside it. The other compression that you could have would be isentropic. And I won't go through the derivation, but isentropic means that it's to the power k, right? To the power k. This is rho density to the power k equals constant. And K happens to be the ratio of the specific heats at constant temperature and pressure. Doesn't matter what that is. That's a thermo. For air, K is about 1.4. And so it's different. So isentropic means that you take your bicycle pump, you put that expandable foam around it, so it keeps all the energy that you create in it. So as you pump it, it gets hotter. It keeps all that change in temperature in there. And the temperature, the pressure density changes that you get are controlled by that. So there's two different forms of compression that we might want to be interested in. So that's all we need to deal with for that. What else? Okay, that's all we need. So we're kind of up to where I wanted to be. So I'll zip through this. I don't like using this. They're not very pretty notes anyway. Not that that's an issue. So we're kind of here, I suppose, right? So we want to talk today about compressibility. We want to talk about wave speeds. We want to talk about viscosity. And we want to talk to surface tension. So we're going to have to move a little bit. Compressibility. Seems a bit esoteric. So compressibility or modulus. We said last time that the book calls modulus E. I'm not sure if it calls compressibility anything, but I call it beta. And so they're reciprocal each other, as it turns out, just 1 over. So the units have to be the reciprocal. What we could do is we know that density is equal to, I'm loath to do this derivation, density equals mass over volume by definition, kilograms per meter cubed. And so we could also write that as being equal to mass is equal to density times volume. We could also differentiate this with respect to pressure. And if we do that, then we have to split these variables, so it becomes d rho dp, pressure, density over pressure, times volume, plus density times d rho, no, dv dp. If we divide both sides by v rho, as we can, and I guess we have to divide this by v rho. I know it's getting complicated. Then if we simplify that, we get dm dp 1 over v rho is equal to d rho dp. I'm already regretting doing this. 1 over rho 0. See, these cross out. Plus dv dp 1 over v0. So if we take a volume, that's this, and we put a pressure on that volume so that the volume reduces by some amount. So this volume here is V0. This volume here is dV. So this is our cube. So what we're going to do is we're going to take it and we're going to apply a pressure to it all around. So by definition, if we apply that delta pressure, perhaps I'll call it dP, then the pressure in here changes by dP as well, just by statics. Take a balloon, put it under water, the water pressure at the bottom of the swimming pool is higher, the pressure in the balloon has to have increased, and you'd probably expect that the balloon compresses a bit and gets smaller. So that's compressibility of the gas. And so all the mass that was in the balloon before is still there. So the change in mass with pressure within the balloon is 0 when you put it down, right? There's no mass, no molecule of air has got out. So this equation has to equal itself. And so if we look at that, then that's exactly what this compressibility is. It's a pressure, change in pressure, change in volume over a reference volume. We can write it as a change in pressure over a change in density for a reference density. They're equivalent except for a plus and minus sign. The only reason for the minus sign is that if you increase pressure, so if this is positive, then you know that the volume will go down. So in a quadrant of a change in pressure with volume, it's in the positive quadrant. A change in volume with pressure is in the negative quadrant. This is what I mean. So in other words, too much, right? I knew I shouldn't have embarked on this. Sorry, that's not it. Yeah, change in pressure. Change in pressure is positive. Change in volume or volume goes down. It's in the negative quadrant. So this is negative. And so we want our coefficients to be positive. So we just multiply it by a negative sign. We could do either. So this equation here describes compressibility. So what we can do with that is that we can note that in terms of modulus is equal to, what was it? dP over d rho 0. We have the ideal gas law, which is P equals rho RT. We do dP d rho equals RT. And we write density here in terms of the ideal gas law. It's going to be rho is equal to pressure over RT. So if we have this, if we make this substitution and this substitution, then we end up with the modulus of air is equal to rho RT. No, sorry, not this, right? It's underneath here. RT multiplied by P over RT. Long derivation. I mentioned it on the first day, I think, or perhaps Wednesday. Pressure. So the modulus of air at whatever pressure it is, roughly in the range that we'll do, is the same as the pressure we find ourselves. So the modulus of, what's the modulus of the air that we're sitting in right now? Absolute pressure. Right? And so that might seem esoteric, but the use of it is that we can get wave speeds. Oh, I should also say, so before I do that. So air is a gas, and we can use the ideal gas law. So this is for air. Everything we've done so far is for air. For liquid, water, this is a gas. Then the equation that we have, which is that the modulus is equal to the change in pressure divided by the change in volume over initial volume, right, which you could get from this. We can measure that. So you take a block of rock or a block of some water, you put water in the balloon, you put water in the balloon below the swimming pool. At the bottom of the swimming pool, it's at a different pressure from what it was on the surface, higher you think, because your ears pop. So the water would have compressed some small amount. If you can measure that small dV from the volume of the balloon, then you're able to calculate exactly what this is. You know what the pressure change is by going down 2 meters, 6 feet in the pool. And so for compressibility of a liquid is typically constant and has to be measured. And we said last time that for water, Not a bad number might be 2 gigapascals. For rock, not a bad number might be, I said 10 to 30 gigapascals. And for air, we know what the modulus is as well. Compressibility is just reciprocal of that. So 1 over 101 kilopascals, whatever that would be. I guess 10 to the minus 5 pascals to the minus 1. So perhaps worthwhile writing that. Equals 1 over E. And so for air, it would be 1 over 10 to the 5 pascals, which is 10 to the minus 5 pascals to the minus 1, which is newtons, units of newtons per meter squared, minus 1. Okay. I see a wave on the horizon. I don't know, has anyone been timing this? I've lost track of time a bit. Just in time. All right. So it might seem a bit esoteric that we've talked about compressibilities. One reason we talk about compressibilities is because the wave speeds in a body wave maybe you call it C, I think the book calls it C, is equal to the modulus divided by the density square root. Standard result. I won't derive it, too long. So for air, the wave speed is the speed of sound. You're listening to me. And so for air, we know the modulus. The modulus is 10 times 10 to the 4, 10 to the 5, right? Density of air, 1 kilogram per meter cubed, roughly. 10 to the 4, this is in newtons per meter squared. We know that 1 Newton is the force required to give 1 kilogram an acceleration of 1 meter per second squared, by definition. So you could substitute for that. I'm not going to do it. But if you do the math for this, the speed of sound in air is equal to square root of 10 times 10 to the 4. The reason I wrote it like this is because that's easy. Square root of 10 is 3. Square root of this is 10 to the 2. So this is roughly 300 meters a second, which equals about 600 miles an hour. Which is about right. Passenger planes fly at 500 miles an hour. It's slower than the speed of sound. If you fly faster than the speed of sound, you build up a bow wave, just like Missy Franklin, where you can't get rid of the energy in front of you, so you have to build a much bigger, stronger plane to resist that. And you also have to provide much more power to push through that bow wave, just like swimmers don't want to make the wave. And so the rate at which you're hearing me is at the speed of sound. You could do the same things for rocks. I won't do it right now, but it's relevant to this particular example that we're going to look at now. The celerity wave. So wave speed in a body wave means that if I come along to the end of your bench or your desk and I hit the desk, bang, if you have your hand or your head on it, if sleeping, you'll feel that wave transmitted. It'll bump you up a little bit. If I shake it like a shear wave, it'll travel at something like the speed of sound in that material. It's governed by the modulus of the material and its density, just like this equation here. The shear wave travels at roughly half the speed of the P wave, so-called. So these are body waves, and the sound you're hearing is a body wave also. It's coming directly to you by compressing the air in front of me. It's like shunting a train. You hit the back train, it goes boom, 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 boom. That's exactly how the wave travels. If you look at celerity waves, which is what you're looking at in your screen, which is a wave on the ocean. So the wave doesn't actually move, but its effect moves, right? So this point doesn't move, this just rotates as it goes along. The celerity wave speed is equal to g z square root. And z is just the depth of the wave. And so if for Kamaishi you use 1,000 meters and you use 10 meters per second squared for gravity, and you use 1,000 meters for the depth, not sure what's happening on the screen, don't get distracted, then you end up with, this is 10 to the 4, so this is about 100 meters a second. Much faster than you think, really, right? 100 meters a second. Usain Bolt, or whoever won the Olympics, it wasn't the American guy, it's 9 seconds to run 100 meters, right? Of that order. And so it's actually kind of a surprising size. So the relevance to what's going on here is that now, 20 minutes later, if we look at Kamaishi, this tsunami, so-called harbor wave, is it marches relentlessly in. It's come away from the source of the earthquake. It's traveled at the wave speed, which is the celerity wave speed, which is roughly 100 meters a second. The earthquake is about 100 kilometers offshore. So 100 meters a second means 10 seconds to go a kilometer, 100 kilometers in 1,000 seconds, 600 seconds would be 10 minutes. So it's about 18 minutes, something like that. And so it takes 18 minutes for this wave to inexorably reach the Kamaishi port. It's not a breaking wave, it's just a tidal wave. It's called, tidal wave. It's called a tidal wave. The strict translation in Japanese is a harbor wave. We're in a harbor, and it's a wave that comes in, and it's just a rise. And so the best defense to a tsunami is to find a high spot, like a garage, multi-level garage, and take refuge. And so that's what's going on there. So you can see, well, you'll be able to find it online. So early on, looks like that was at 20 seconds. You still see boats going out to sea. So anyway, so I'm going to stop it there and not distract from what we're doing. So the stuff in your blah, 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 we've done this. So this is the idea. You have the earthquake. It's 100. The earthquake is in the Japan Trench. This is where, this is the trench. This is where one plate goes under Japan, melts, causes Mount Fuji. This is something like 100 kilometers. So if you use the ideas that we had, that getting you wave speeds from the moduli, we would know that the wave speeds, we've called this modulus in our particular one. I just put this on last night. For rock, water, air, and the celerity waves, this is the wave speed, 100 meters a second. If you look at the wave speeds, I guess it would go here. And so the idea is that you have ocean bottom sensors. Those sensors are attached to the land by an electric cable. A signal, once it's shaken, goes to land at the speed of light on the electric cable. So as soon as it happens, and you can process the signal, you know that an earthquake's occurred 100 kilometers away. Now you have a warning. So the P wave travels at something like 3,000 meters a second. So that will travel 3 kilometers a second for 100 kilometers, so about 30 seconds. So the P wave will arrive 30 minutes later. Get the hell out of the building. P wave doesn't hurt very much. The S wave, the skipping rope on the ground, which shakes laterally, is the one that destroys the buildings. Half the speed, so that arrives in 60 seconds. We're already out of the building. Hopefully everything's attached so nothing falls on us as we run out the door. And then the celerity wave will come in something like 18 minutes later. And you hope that by that time you've gone up from the coast, up on a relatively mountainous promontory in Japan, which is a mountainous island, to be able to save yourself. So wave speeds are important in this context. They're also important in the Missy-Franklin context, in that you want the wave speed, the bow speed ahead of you, to be faster than you're swimming, because that way it will travel away from you faster than you're swimming into it. If you're swimming into it, then it will rise and it will act as a resistance against you. Blah, blah. All right. Okay. 15 minutes left. I think I'm going to have to add, I prefer to do these things. Whoops. I'm going to add a page. I might add 2 pages, actually. I don't think we'll get through 2. All right, the last couple of things to talk about. I'm trying to make it interesting for you. I know it starts becoming like a drinking out of a fire hose. 2 final topics to deal with. One is viscosity, which we talked about but haven't defined. Doesn't want to do it. And the other one is surface tension. So viscosity is exactly this. So take 2 plates. We want to measure what this viscosity is. You know what viscosity is. You know that if you have treacle or honey, pour it out, it's viscous, it's slow moving. Water moving out would be faster. Air would be even faster if you could see what's going on. So it measures the rate at which, the resistance to flow, if you like. So what you could do is you could take 2 plates, sandwich between those 2 plates a fluid, a liquid, has to be a liquid, and you move this plate at some velocity in the x direction, and you measure a change in velocity in the y direction. So initially, before you start moving the plate, the profile of all these points across that fluid are straight. And as you move that plate at some velocity, Vx, then you know that the fluid is attached to the upper plate and also attached to the lower plate, but the lower plate isn't moving. So the velocity profile will look like this. It'll be velocity x at the top, and the velocity at the bottom will be 0. And this is what we call velocity, viscosity. So if you plot, for example, dvx dy, you could also write this as delta y if it makes you feel better. This could also be Vx over delta y. Whatever the Vx equal to the top, I guess, is what I want to say. Don't need this anymore. And if you write on here the shear stress, so to do this, you'll have to apply a shear stress tau, or a force S. So imagine attaching a force onto this upper plate that has a given area. I can't draw in perspective very well, but if you can imagine this plate sitting on top of the fluid like this, it would have an area, which would be this area here. And we know that Newton's law of viscosity is that a shear stress is equal to a shear force divided by the area on which it acts. So this is the force you're pulling with, force S. And the shear stress is just the ratio of those two, and that's equal to a dynamic viscosity, mu, multiplied by the rate of change of velocity in the x direction, divided by dy. And so clearly, if we move this at apply some force, and we know what this force is, if we know what the area is also, we know what the shear stress is. So presumably we can get this. And if we measure the velocity at which it moves at, and we know how thick the layer is, we can calculate this. So we end up with some point, some value of tau and some value of viscosity. So this is the point we're interested in. If we, let me just draw a line through those. If we double the shear force that we apply, then we double the velocity at which we're traveling, where this length and this length are the same, and this length and this length. So this is tau 1, this would be 2 tau 1. So this is what's called a Newtonian fluid. It means that as you double the shear stress, you double the velocity it travels at. Some fluids are not Newtonian. A typical one is up here. They don't go through the origin, and they're not constant gradient. The most common one would be a thixotropic one, which would plot somewhere like this. Could be at the same gradient as this or not. This is typical of drilling muds. Put it in a hole. If you leave it there, it's got bentonite in it. You want it to push the hole, a drill hole open and keep it open. If you don't move it, it becomes kind of a solid. It means that you have to keep on applying an increased shear stress to it. It doesn't move, it doesn't move, doesn't move. All of a sudden it starts moving. And it has this yield stress before it starts moving. It's just a characteristic of one of these fluids. And so that's the materials there. The materials we'll deal with in this class are all Newtonian, and we'll use what we'll deal with, which will be Newton's law of viscosity. And so, just like modulus, it's a measure of a property of a fluid, liquid or a gas. It's a measure of the resistance, the frictional resistance of a fluid to flow, and we can use it in lots of things as we go down the pike. Okay? Do I want to say anything more on that? No, I don't. There are, in this, some examples. You can go through them to see how you'd use it. Quick example here. I won't go through them today. The one thing that comes out of it, another reason you might want to use your book, is it has tables in them. If you look at the dynamic viscosity of water, where are we? Water is here. It changes with the temperature. At room temperature, the viscosity of water is something around 10 to the minus 3 Pascal seconds. Those are the units. The viscosity of water decreases as you heat it up. You'd probably think that becomes less viscous. Gases are roughly 2 orders of magnitude less viscous. 10 to the minus 3, gases are 10 to the minus 5. And the interesting thing about gases is that they get more viscous as they get hotter because the molecules get excited and bounce around and behave that way. And there's an example, a viscosity example here. You can probably find better ones in the book. And the final thing that we'll talk about today is surface tension. Let's see if this works.
So when you're out on Thirsty Thursday and you want to see what the alcohol the vinometer. So when you're out on Thirsty Thursday and you want to see what the alcohol content is of your beer, or with friends, and of course you
What a handsome guy,
you're still
and
friends,
so young.
you can put it in a vinometer. Vinometer is just something that gives you the alcohol content of liquids. And so what you do is you put the liquid in here. If I have water, I put it in. It fills up this little capsule at the top. This is a capillary tube which has, you can
see the line?
The hole through it, which comes out at the bottom. You blow until water comes out at the bottom, so you fill up this capillary tube, and then you stand it upside down. You stand it upside down, and now this is open, and you can look within this tube, it's graduated on the side, to give you the alcohol content, which is the height to which this will stand up within this tube. And so It's really controlled by the surface tension, which would be across the top of this tube, open at the bottom here, which is at atmospheric pressure, and so it's a direct analog to the system that we'll look at right now.
We will indeed. Believe me. Surface tension. So, interesting application for that, I guess. So it's surface tension, of course, is the thing that allows bugs to walk around on top of water. We'll look at it in terms of a capillary tube. If you put a capillary tube into water, slightly different from the geometry we looked at before, you know that there's a rise of the fluid in here. And I'll call this sigma for a force. I'll define this as a height rise, h sub c. And I'll define this in terms of a diameter. And so what we'll find out is that as we move horizontally in a fluid, if we move from this point to this point here, and we can get in a connected path without passing through a solid, which we have, then the pressure at this point has to be the same as atmospheric pressure here. So we can cut this system off at the bottom and look at it actually just like the venometer. And so a simplified system for this would be to look like, well, I don't want to do a not a very good drawing. But this is the force that's pulling up here, which is at sigma, and it's all around the contour. And so the vertical component of that would be, if this angle is theta, this would be sigma cos theta, all the way around. And there would be the weight of this acting downwards. And what we can do is we can do a force balance up and down. And so the force balance going up and down would be, the weight has to be equal to this force here. So pi d would be the circumference, right, around here. And we have a force acting upwards of sigma cosine theta, right? That's what's pulling it upwards. And W is going to be equal the volume multiplied through by the density times gravity, which is going to be, the volume is hc pi d squared upon 4. These two together are the volume times density times gravity. And so if we equate these two, this is the volume, it's not divided by volume, right? So we have pi d sigma cosine theta, you can probably do this faster than me, is equal to hc, and I'm going to divide it through by those components, pi d squared rho g. It says that the height rise is going to be equal to, we lose one of these, we lose the pi's, is equal to sigma cosine theta divided by rho g. The book also uses, and I also use, the unit weight, which is gamma, which is equal to rho g. Just terminology. So this means that the height rise of the fluid into the capillary tube is proportional to the surface tension. Higher surface tension means it gets dragged up into the capillary higher. And I left out a D somewhere, right? And the smaller the diameter, the higher it goes as well. You know that intuitively. You have a 1-inch tube, you put it in water, you can't see a height rise. You have a 1 millimeter tube, you put it in water, you'll see some height rise in water. This is what the tube would look like for a wetting fluid, water. For mercury, it would be concave downwards, as you probably know also. but you can use this to measure, so you could use the height rise, measure the height rise if you know the diameter of the tube to calculate what the surface tension is. Just like in the case of viscosity, the viscometer, a plate moving over a fluid, if you measure the forces applied to that plate and its velocity, you can calculate this useful parameter which we'll want to use, which is the viscosity. In this case, you can calculate this useful parameter we'd like to know, which is the surface tension, just by measuring that. It's important in oil reservoirs. Oil reservoirs have water and oil. They don't mix. They have a tension between them, an interface between them. Some rocks are water wet, some rocks are oil wet, and the behavior of them are very different. Environmental systems engineers cleaning up hazardous waste sites. Free phase gasoline with water in the ground also is immiscible. And so that's that. What else do I want to say? I don't want to say anything. I think you should have a good weekend. Questions? All right, so as with every week, so the assignments are live. You should have everything you need to cover the first assignment due next Thursday at midnight. No class on Monday, but the material on Monday you might want to look at. There's an extra credit quiz online. You might look at that material before Wednesday because we will jump straight into 2.2 on Wednesday. Up to you whether you do or not, but that's the deal. So get yourself some extra credit. The extra credit quiz is open on Monday. They stay open for 2 class periods. Mondays close on Fridays, midnight, etc. Anything else? Great. Have a great weekend.